Welcome, everyone. As we're getting settled here and folks are joining, please sit tight. We'll get started here in 2 or 3 minutes. Give folks a chance to get into the webinar. We appreciate you being with us from wherever you are. So that's either good morning, good afternoon, good evening, and in some cases I see deep into the night. So again, we really appreciate your participation today. So again, just give us another minute or so and we'll go ahead and get started. While we're waiting for folks to join, I want to say we're all getting very excited for the IWCS 2024 in Providence in October. We have a deadline coming up in early April for abstracts. So we hope that with all of your work and your company's contributions to our industry, that you're giving strong consideration to putting in a technical abstract and present yourselves at IWCS. Will really be good exposure to your colleagues, your customers, your suppliers, to let you know, let the world know how important the work is that you're doing. So again, for those of you just joining, we're just waiting a moment or two here for everyone to join, and we'll go ahead and get started. All right, there will always be a few late folks, but again, welcome and thank you for joining us today in our IWCS webinar series event. My name is Dave Cadu, and I'm your CEO and Director of IWCS. And I'll be your moderator today for this excellent presentation. A few housekeeping items, as many of you already know. As an attendee, you're part of a larger audience. So during the presentation, you will be in listen-only mode. And also, we are recording this webinar for rebroadcast on our website. We capture all of our webinars and post them on our website, so you can go back and review them, and either this webinar or the ones in the past. So please feel free to share that information with your colleagues in case they've missed this webinar and wish to see it, or you wish to see it again. Also, we encourage you to enter your questions during the presentation. As a question comes up in your mind, please type that in the chat function. The chat panel, once you open it, should be on the right of your screen. And after typing in your questions, be sure to hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. Our webinar series event is hosted by the Cable and Connectivity Industry Forum. And today we welcome Huimin Cao from Covestro. She is a science fellow at the Science and Technology Group in Illinois, USA. Dr. Cao will be presenting her paper on UV-Curable high temperature resistant dual layer coating systems for specialty optical fiber applications. Very important technology and very useful in today's environment for new fiber optic designs. Dr. Cao is again a science fellow at their Science and Technology Group at Covestro. Her expertise is in material science, with the focus on material properties and structure property performance relationships. She has extensive experience on UV-curable materials for optical fiber applications. So again, we welcome Huimin to present at today's webinar series event. So thank you for being with us, and go ahead.
All right. Thank you, David, for your kind introduction, and thank you for inviting us, giving us this opportunity to reach more audiences after IWCS about this topic that we believe is very relevant to the fiber optics industry. And welcome everyone for attending this webinar. Attending this webinar by Covestro as the major supplier of UV-Curable materials, especially optical fiber coating materials. And we have good news to share that we are introducing this newly developed UV-Curable high-temperature resistant dual-layer coating system for specialty fiber applications, which is the next generation product to our current single-coat high-temperature coating, which is known as Desolite DF999. And DF999 has been successfully used for specialty optical fibers with proven high temperature performance in the past 15 years. But as a single layer coating system, it does inherit some intrinsic performance gaps, which I will show a gap analysis next. And you will see the solution to overcome these gaps is to develop a dual layer coating system. However, due to the high technical challenge for the dual layer coating system to match the thermal stability of a single coat, especially with the much softer primary coating, this attempt has not been very successful in the past. To explain the design of our new dual layer system, I will show a failure mode analysis of how conventional standard coating would fail under this high temperature aging, and how we designed our new coating system to avoid these failure modes. The high temperature stability is characterized in the lab with film samples by a commonly used weight loss measurement by TGA and the mechanical properties by DMA. This presentation only covers the film study, but the conclusions were drawn in the end, also based on successful qualification trials from fiber manufacturer. Here's this DF999 single coat was introduced in 2009, and it has been successfully applied in a variety of specialty fiber applications under harsh high temperature environments. It specifies here that suitable for long to mid-term use at temperature range of 100 to 150 or short-term use at high temperature range of 150 to 200 degrees C. Several papers from our company at that time is DSM Desotec, around that time period describe the development of this single coat UV curable material. And it is based on a non-urethane acrylate chemistry. These papers showed that the typical urethane acrylate chemistry used in the regular optical fiber coatings suffer from severe coating degradation due to urethane linkage, more prone to break under high temperature, and lower the modulus, more severe the weight loss, which is used to represent the degree of polymer degradation. And in comparison, the non-urethane-based chemistry is much more stable and not that sensitive to different level of a modulus. DF999 was designed at around 700 megapascal, which is a medium-high level, appropriate as a single coat. For gap analysis, if you compare the single coat DF999 with a standard primary and secondary dual layer coating system, DF999 for sure has much better thermal stability at high temperature, but there are intrinsic performance gaps compared to a dual layer coating system, such as the strip force being much higher, and this is because the 60 micron single coat requires much higher force to buckle and break than stripping a dual layer coating system, which is with a 30 micron of a much softer primary coating. Another important aspect is microbending performance. As well known, the best protection to fiber microbending loss is with a dual layer coating system, which combines the buffering effect from a soft primary coating and shielding effect from the hard secondary coating. Of course, the single coat in nature is worse than the dual layer on microbending performance. So it has been clear to us, and also from customer voices, that the high temperature resistant dual layer UV curable coating system is highly desirable. Here is how we mapped out the performance space of this new dual layer coating system. It should cover the same high temperature space as the single coat DF999 from 100 degrees C to 200 degrees C, with the primary HTP designed at the low modulus level, but slightly higher than the regular primary. And this is to balance the thermal performance and the microbending performance. The secondary coating, HTS, is designed to the same high modulus level as a standard secondary coating. And this is to benefit both the thermal performance and the microbending performance. And before we dive into how we designed our new coating system, it is important to understand the general polymer thermal degradation mechanism. At the high temperature range that's relevant to this specialty fiber application, at least higher than 100 degrees C, hydrolysis of polymer degradation is no longer that relevant because lack of moisture at those extremely high temperatures. So the main degradation mechanism is from thermal oxidation and plus some thermal pyrolysis. And thermal oxidation is a free radical chain reaction process where oxygen not only played the role of propagating the radicals, but also plays the role of auto-acceleration by chain branching. Through a hydroperoxide decomposes to two radicals. And one of the radical is this oxy radical, which is very unstable and readily goes into chain scission. And the consequence of the chain scission is breaking down the cross-linking network of the material, making the material weaker. And as the termination of this chain reaction, when two radicals combines each other, it can also form crosslinks and this additional cross-linking reaction will make the material brittle. And between these two effects, which one dominates depends on the material network structure, which I will discuss next. And this simplified diagram explains why developing a low modulus primary coating for high temperature durability is so much more challenging. If you assume same number of chains breaking down from the thermal oxidation process, the softer primary coating with much less crosslink points will suffer much more quickly, losing coating integrity than the high crosslink density secondary coating. And this is why primary coating is the weakest link when developing this dual layer coating, high temperature coating system. And here's the actual illustration of how a fiber coated with a conventional urethane acrylate-based dual layer coating system degraded under high temperature aging. And picture A shows a pipe fiber just under 1 day of 180-degree aging. And even just from the hand handling of this fiber, it easily formed defects in primary coating, which are shown as cavities. And this is because the primary coating at this point already turned into a soft gel after the network broke down from the chain scission process. Also because the weight loss from primary coating is much more significant than the secondary coating. So the primary coating layer is actually under a high triaxial tensile stress, which makes the cavitation easily formed and widely open as an empty voids due to this triaxial tensile stress. And with the primary coating losing integrity, this fiber can be easily tube off by hands. Just simply taking off both layers of a coating as a coating tube by hands and leaving a lot of very sticky residues of the gel-like primary coating layer on fiber. This picture B is the same fiber when winding into a small coil after 5 days of 180-degree aging. And when unwind this coil back to be straight, this fiber was observed with the glass completely shifted to one side. So this bottom side has no primary coating at all, and all primary squeezed to the upper side. And this is because this is the result of even under this very slight winding stress, the glass was already pushed completely to one side because the primary coating is no longer elastic medium, but behave more like a liquid, so it can no longer hold the glass in place. Another important observation is this fiber, after 5 days of 180 degree of aging, the coating layer actually can no longer easily tube off. It was very hard to strip off, which means the primary coating at this point is no longer a soft gel compared to the first day, after the first day of 180 degree aging. It turned into a harder material. This phenomenon can be clearly seen in this chart that's following the in situ modulus change of the primary coating during the aging process. The red line started at a normal modulus level at around 0.6 megapascal, started to drop severely in the first couple of days to near zero level, which means really it is very close to liquid, and then started to rise a little bit in the third day, and then sharply rising after 5 days. This means the shift of the glass in this coil occurred at the first couple of days, and then it was fixed into this position with longer time of aging when the coating turned harder. So I remember David discussed with me after my talk at IWCS. So this means if you do a test in the lab, for example, a strip force test at high temperature aging, and if you miss this early stage of a coating turning into a gel, and you waited several days when you did the strip force, when it seems to be normal above the spec, you may think the strip force was okay. After a period of time, it was actually not okay because you missed the point that with the coating already turned into gel, the strip force would have turned way down below your spec. Right. And remember, these are accelerated lab tests at the temperature much higher than your application temperature. So at your actual application temperature, there might be a long period of time that coating broke down into a gel-like material. And this is the most risky situation in the field because the primary coating at that stage has a high risk of forming cavities, develop delaminations, and which will cause attenuation increase. And that's definitely you don't want to see. And even when the material turned harder at a later stage, you should not consider this is a harder material. This harder material means recovery of the coating property, because this aging-induced cross-linking process occurred after a severe transition when the network already destroyed. So the termination process will form very short chain crosslinks, which means resulting in a very fragile material. Let's look at the secondary coating, the blue line. The secondary coating did not show a transition dominated stage. The modulus rises and elongation actually decreases with aging, which leads to an embrittlement. Picture C is the fiber after 5 days at 200 degrees C, and after manual handling, the secondary coating showed cracking. And this is an indication of embrittlement. So in summary, at high temperature, soft primary coating undergoes first a transition process, dominated process, and then later a cross-linking dominated stage to a disintegrated fragile material. And hard secondary coating undergoes mostly a cross-linking dominated process into a brittle material. With that understanding, we designed our new dual-layer system with the non-urethane acrylate chemistry to avoid those failure modes. The HTP is designed at the modulus level around 5 megapascal, slightly higher than a regular primary coating to avoid the severe network breakdown from transition, but still significantly lower than the single coat DF999. to improve the microbending performance. The secondary coating designed at the same modulus level as a regular secondary, but with a TG design lower than the regular secondary coating, but more similar to the single coat. And this is to avoid the embrittlement after aging. And here is a dynamic TGA weight loss comparison of these coatings, which is a quick way of ranking the thermal stability of different materials. And the onset temperature, or called oxidation induction temperature, OIT, is an important parameter to rank the thermal stability of different materials. As you can see, the HTP has only a slightly lower onset temperature than the single coat, and it is way higher than a standard primary. And HTS, of course, is even slightly higher than the single coat and way higher than the standard secondary coating. And one thing to notice is this says here the test condition airflow rate of 50 milliliter per minute for this TGA test. And this is an arbitrary test conditions set for TGA experiments. As in this comparison, you can see the air or nitrogen condition varies a lot on the weight loss behavior, which is understandable because the mechanism is highly involved in thermal oxidation. But also notice, even if all in airflow condition, the rate of the airflow makes difference too. And higher the flow rate, lower the onset temperature. And if the flow rate is very slow, such as 1 milliliter per minute, it's actually very close to nitrogen condition. And the indication of this is the coating degradation behavior is very sensitive to the local oxygen concentration sitting on top of the coating. So when the oxygen is consumed from the coating thermal oxidation reaction, it needs to be replenished from fresh air to maintain the reaction rate. So this finding could lead to an expectation that in an actual field condition, where these fibers are often in a very high fiber density cable where there is not much free space of air, the airflow also restricted by the cable jacket, the actual coating degradation rate in cable structure could be much slower than the predicted from these lab TGA film tests. So the purpose of this lab experiment is mainly for ranking the relative trend of thermal stability of different materials. But even with that expectation, you still shouldn't run the risk of using a conventional urethane acrylate-based coating for your actual application. It will still cause field stability issues, durability issues in the long term. These specially designed high temperature resistant coatings is highly desirable. It's just to show that whatever we predicted in the lab test is not being interpreted as an absolute value, but as a relative ranking sense. This chart shows the isotherm TGA results held at 260 degrees C, where the HTS has a slightly slower weight loss rate than DF999, and the HTP is actually much better than the regular secondary coating. And consider its modulus is 100 times lower than the standard secondary. This is quite remarkable. And of course, it's significantly better than the standard primary, which cannot survive at all in these extremely high temperature conditions. It's very risky to use this kind of coatings in high temperature environment. And why we're testing in this extremely high temperature condition? It is for Arrhenius study, where you do accelerated lab testing at temperature range much higher than your application temperature. In our case, up to 300 degrees C, which will make it possible as a short-term test. And based on Arrhenius equation of a straight line fit, you can predict the lifetime into your field application at lower temperature. And the Y is the log scale of the time when reaching a 25 weight percent, which is defined as a failure criteria commonly used in the literature. As you can see, the HTS performed the best, even slightly better than the DF999. And even the HTP is still lasted longer than the standard secondary coating and significantly better than the standard primary coating. Based on this study, the lifetime prediction is drawn in this chart. For example, at 140 degrees C, the standard primary only lasted a couple of days, losing 25 weight percent, while the HTP predicted can last almost a year. And keep in mind, this is only valid in a relative sense based on this weight loss criteria from film study. For coated fiber, it is perfectly fine if you want to use different performance criteria for your lifetime prediction. You can use strip force, attenuation increase, or detection of any coating defect formation, and you can decide the lifetime, the upper use temperature for your short-term temperature, for your short-term application, or the upper use temperature for your long-term application. Here is prediction based on this film TGA study. Now, this test is with the dual layer film sample where the drawdown was made with 1 ml of a primary plus 1 ml of a secondary on the top. And this is to simulate the dual layer performance on fiber. It shows that the HTP and HTS weight loss is closely matching a single coat DF999, which significantly shifted higher than the standard primary and secondary. The predicted upper use temperature for 20 years of a lifetime listed in this table, for example, for DF999 is 114, but actually, as reported in the literature with the same method of a TGA and the 25 weight loss, on fiber prediction for DF999 is 130 upper use temperature for 20 years. So this gap is expected because the fiber testing, the coating is only exposed to the air from surface side, one side only. Instead of the film test, the bottom is just loosely sitting on the pen. So the sample, this very small sample, is exposed to air from all sides, top and bottom, left and right, and it's all sides. So the film test is a much more severe test than the fiber. So once again, all these predictions is only for relative ranking purposes. Another traditional test is the oven testing. After 5 days of 100 degrees C oven aging, the standard primary turned into completely dark. And it is a char-like material, which is probably only carbon left. There's no integrity at all of this coating after 5 days of 180 degrees C. It cannot peel from the aluminum pan as a film anymore. It just chips off. And the HTP is still a very nice film, only with some degree of a yellowing. And the HTS is not only a very nice film, but also non-yellowing at all, which is better than the single coat. And it is, if you look at the weight loss from this oven testing, at the high temperature ranges, it shows clearly that the high temperature coating are much better than the standard primary coating and secondary coating. But it's worthwhile to note that at low temperature range, such as 125, 150, the standard P and standard S did not appear to have a higher weight loss than the high temperature coating. And this is only the case in oven testing, not in TGA. Because in TGA, the standard coating, even at this relatively low temperature, was still shows the conventional coating higher weight loss, significantly higher weight loss than the high temperature coating. And the difference is in the oven, that at these relatively lower temperature, there still might be some moisture content left, while in the TGA is dry air. So the weight loss from the oven test is no longer a proper parameter to evaluate the coating degradation at these relatively low temperatures. And the conventional coating may undergo even severe, some hydrolysis process also going on. As a result of that, you will see in the next slide that the property measurement actually started to see severe degradation on the traditional coating, regardless of very low weight loss. Here is how we characterize the thermal property change with the aging. It characterized by DMA by looking at the equilibrium modulus change, which represents the cross-link density of the material, and the 10 delta represents the glass transition. For primary coating, the standard coating, primary coating modulus going down as expected to almost 0 before it goes up. And high temperature coating, it started higher already. It comes down a little bit, but far from being risky of disintegration type of range. It's still very nice solid coating. And then the rest of the aging time, it slightly goes up, but still way lower than the single mode type of modulus. The high temperature HTS shows a remarkable stable of equilibrium modulus, similar to DF999, very stable and much better than the stability of standard secondary coating. The TG shift is also much lower than a standard secondary coating, which will result in a much better retention of a material toughness, avoiding the failure mode of embrittlement, secondary embrittlement at high temperature. So in summary, we have analyzed the different failure modes of conventional primary and secondary coating and designed our new primary coating to effectively avoid these failure modes. The thermal stability has been tested closely matching single coat DF999 from film TGA from DMA test, and fiber testing, which is not discussed in this paper, also confirmed its superior thermal performance at high temperature. And the fiber trials from qualification also confirmed that the new dual layer coating coated fiber provided much improved lower strip force and much better microbending performance than single coat coated fiber. So this new high temperature resistant dual layer coating system, HTP, HTS, has been successfully qualified from fiber and cable testing for specialty fiber applications at this high temperature environment. And if you're interested in testing this new coating system for your application, please feel free to scan in this QR code, which will give you a link to our webpage, and you can learn more about our technology and how we provide solutions to the optical fiber industry. And you can click here, those links, which will reach to our business group. Also feel free to contact me with my email address, and I'll be happy to answer any questions. Thank you. Back to you, David.
Huimin, thank you as always for your great contribution and important work to improve the stability and integrity of fiber in a variety of applications. Again, I invite any of the attendees to enter some questions if you have them. But for what types of applications are these dual layer high temp coated fibers designed for? I mean, are they currently commercial in any particular applications that we can relate to, or is it a wide variety? I mean, it's indoor, outdoor.
These are information that we have only very general information from our customer. Of course, the very detailed application can only provide by the industry. What are they using our current DF999 for? For example, the aerospace application, satellite, this automotive is what we heard most. High high power laser is another
Right.
very popular application. The oil rigs and some mechanical devices that will be under a high temperature type of environment. And of course, different customers may have different specialty application, but DF999 as a single coat has been commercially used for these applications in the past 15 years with very good feedback. And this dual layer coating is just to overcome some performance aspect in terms of strip force, in terms of optical performance, but maintaining the thermal stability of as if a single coat.
Yeah. In addition to the mechanical integrity that you were describing, is there also any chemical resistance, any times of fluid resistance in some of these applications might be required?
The fluid resistant, this high temperature coating, we expect it should be even better than traditional coating. But the traditional urethane acrylate-based coating already provided very good chemical resistance towards typical chemical environment, whatever in the cable or the gel immersion type of test. And this new HT high temperature coatings should be even better because the primary coating now designed at even a slightly higher cross-link density.
Right. Yeah, that makes sense. How are the dual layers for the coatings applied to the fiber? Is there any new processing equipment necessary?
There are generally two different categories of processing in terms of a dual layer coating system. It's either wet on wet or wet on dry. And our new coating system can be easily applied as a wet on dry. And with wet on wet, I didn't show the rheology profile, but you will see at the selected temperature range, this viscosity of these two coatings are closely matched. So you can also easily do a wet on wet.
Okay. Very good. And do these new secondary coatings add any concerns for fire performance or emissions of anything, whether it be smoke or anything else?
The chemistry of this dual layer coating is very similar to our single coat DF999, and DF999 has been proven as a safe coating material to be used in the field. It's not known, we didn't hear any feedback as a cure coating. It has any diffusion of hazardous substance out. There's no such negative feedback. So we don't expect either for this dual layer coating system.
Good, very good. Do the high temperature coatings have the same curing properties as the standard coatings? In other words, do they work, with the same microwave UV or LED UV?
This generation of dual layer coating, as we just developed, is designed for microwave cure. If in the future customer has more and more popular application with the LED cure, we can have a different version for LED cure. But as for now, it's for microwave cure. And in terms of a cure speed, as far as we know, the specialty fibers is always drawn at much slower speed than a typical single mode fiber for general applications. So we did not have any cure speed issue with DF999, and we don't expect to have any cure speed issue with this dual layer either when it's drawn at a slow speed anyway.
Also, similar to the previous questions, for medical applications specifically, do you expect the coating to be biocompatible? And obviously, the issues again, fluid compatibilities.
That's never been tested.
Right.
That for any medical devices, if it goes into human body, it needs to be carefully examined, evaluated. There'll be actual tests that needs to be done.
Right. Again, for some of these medical devices, what you're thinking are more external types of
Yeah,
devices,
yeah,
operating room devices, right?
yeah, yeah.
Very good. I don't see any further questions. Again, if anyone has a last minute question, please feel free to enter that into the chat. But again, thank you, Huimin, for presenting this, obviously very important and interesting technology. We thank Covestro for continuing to contribute these evolutions in coatings and stabilities of fiber. Um, Again, I don't see any more questions, so let me go ahead and provide again the contact points if you wish to reach out to Huimin after the webinar today. Let me just grab that here. There we go. So again, reach out by email, and I'm sure that she and her colleagues will be very helpful and willing to assist you. Each of these IWCS webinar series events are recorded. So again, please feel free to watch again or provide the information to your colleagues so they can watch the webinar as well in the future. Normally takes about a week or so to have these up and running on the IWCS.org website. The IWCS webinar series conducts technical presentation webinars like this one, along with some sponsored company events several times each month. Our next scheduled technical paper presentation webinar will be on Friday, April the 19th. It's typically the third Friday of every month at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for these events, so please feel free to share our announcements with your colleagues so that they can join in and register as well. Before we conclude, are there any last minute questions? I don't see any. Okay, very good. It's important that we all recognize and thank our IWCS partner sponsors who contribute greatly to the success of the Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you along with our global community. So again, thank you to Covestro as well as these other leading suppliers in our industry for your support in both technical content and innovation, but also the financial contributions to help us bring this to our community. So again, I want to remind you that we're all in preparation mode and excited to bring you the 73rd annual IWCS Cable and Connectivity Industry Forum. Will take place live on Monday through Thursday, October 14th through the 17th at the Rhode Island Convention Center in Providence, Rhode Island, USA. We are right now accepting the abstracts for the technical sessions, technical papers that we hope that you and your company will want to bring to our attention and hopefully enhance the visibility and opportunities for those technologies. So submitting an abstract is quite simple. Just go to our website and you'll see the instructions on what a typical abstract looks like. It's quite brief, and then we'll review those and create the technical symposium in the early May timeframe and present our preliminary program. So please take a look at our website, exhibit your products, present, of course, in the technical symposium, as well as attend. It's always a great opportunity to network with your colleagues around the world and to see the presentations live and in person and ask any questions you may have. So again, it's easy to submit your abstract. And again, please watch your inbox, your social media, and our website to learn more of these exciting opportunities and the information as it becomes available. So take a look at our website at IWCS.org for more event details. And with that, I want to thank you for attending today, and I wish you an absolutely fantastic weekend. Spring is hopefully springing in your neck of the woods, and we look forward to having you join us again in our next event. All the best. Take care. Thank you, Huimin.
Thank you. Bye-bye.
Bye-bye.